Welcome to lecture 25 for multivariable. For better or worse, it's the last one this semester, spring 2020. So today we're just going to talk about our last big theorem, Stokes theorem. You can see old George above me. That's George Stokes, taught at Cambridge, late 19th century. And like so many math theorems, was not the person who came up with this theorem. In fact, the story, as I recall, is another mathematician showed it to him on a train, and then he liked it so much he put it on his exam, and then he put it on his exam the next term, and then he put it on his exam on the next term until students were like, oh, well, I bet Stokes' theorem is going to be on the exam this year, and sure enough, it would be every time. Who knew instructors fall into habits in these things? Anyway, we do want to talk about Stokes' theorem. In order to do that, we got to talk about how we orient a surface and its boundary so that they're compatible, right? Positive orientation of one relative to the other. Here we'll see a brief justification of it and just talk about when it applies, but we'll keep this brief here and work examples in class and see some more consequences of Stokes' theorem. All right, let's just dive in. What does it say? Here it is in its glory. So remember, like all when we analyze integrals, we talk about the where, the what, and the how of our integral. So again, we have two integrals being related in Stokes' theorem, right? So these two computations give you the same number out of this. We've got omega is a oriented surface in R3, right? Well, we've been talking about surfaces. Here, oriented again means there's a choice of direction perpendicular to the surface. So at each point on the surface, we choose a unit normal vector to kind of indicate the positive direction of that surface. And then partial omega, that little symbol that's over here, just is its positively oriented boundary. Now, what does positively oriented mean here? It means relative to the orientation of the surface. This becomes a little clearer if we look at a picture of a general surface. So here's a picture of what's going on. So clearly there's a vector field F, right? That's graphed here in blue, but I just want you to pay attention to the surface here in green. So that's omega, though, as the whole thing is the surface. Notice it's got a boundary. Right? It happens to be in the xy plane in this drawing, but there's nothing that requires that. But here, down here is where the boundary is, right? So along there, right? So that's the boundary of my surface. It extends back here. Do my best to trace this out. Right. Okay. And so now they know that orientation for the surface means, right, a choice of direction, basically. So let's orient, and suppose this guy's oriented up, right? So N points out this way, right, in red. That's going to be what I call the unit normal vector N, indicating the orientation of my surface being in this case, the up direction. So in order for Stokes' theorem to apply, to talk about these two integrals being equal, notice they're both these new kinds of integrals, a surface integral on the left and a line integral on the right. Both require orientation for their respective objects. So if omega is oriented upward, we need to choose our orientation of its boundary so that it's right, so that it lines up so that these give the same number. Long story short, we want to orient our boundary this way. Right? Now it's kind of hard in words sometimes to describe what we mean by which way do you choose to orient the boundary. But if we appeal to our old friend the right-hand rule, that's a good way to think about it. If I curl my fingers in the direction of the boundary, my thumb should point in the direction of the orientation of the surface, right? So you see that in this case, if we follow with your fingers on your right hand around the boundary, your thumb would point up there. It's sort of, if you look down at your surface from above being indicated by the orientation, you should see a counterclockwise curve. The other way of talking about it, sometimes you hear people say, is that when you walk along the boundary in a positively oriented direction, the surface is on your left. All right, so for this guy, right? The surface is on your left here, you know, and that accommodates some cases like when you have a hole in your surface, right? It doesn't, right? It's not simply connected like this. Then you would orient the boundary of the hole the other way, right? Here. Anyway, we got to make sure the orientations line up. Keep right hand rule in your head, and you'll be good to go. Okay, so what does Stokes theorem say? Which two integrals are equal? So on the right, this is our usual line integral of a vector field. So around the boundary, we compute the usual line integral of our vector field f along there. So I see f is graphed in this case right here, right? And as I move along here, I'm just going to integrate how much does that vector field push along this curve. We can kind of get a better view of it maybe from above. Right? What's going on here? And so when we look at the kind of the flow, it looks like there's some positive flow around here, right? We get some positive flow in this direction, and it comes back over here, right? So I probably expect a positive integral for this guy on the right there. Stokes theorem says that integral you get is the same as this surface integral over here, right? So over the surface of the curl of f. Remember, that's a vector field as well. So we can't just say the integral around the outside is the same as the integral inside. That doesn't make sense. But the integral around the outside of a vector field is equal to the integral of the curl on the inside. Particularly, it's a flux integral, which is funny, right? It's the flux of the curl. So, and the reason I put this theorem at the end, it's got the most complicated structure involved. But what it shares with all the other theorems is that you compute something on the boundary of a object. In this case, right, the boundary is a curve around the edge of a surface, and you relate that to change on the inside. So that's the curl of your vector field on the inside surface. We can kind of picture the curl vector field if we just click the box here. Right, it's here in red there. And so this is the hardest one, again, to wrap your head around. Why in the world is this true? Why do I've got flux of a curl is equal to the circulation around the outside? Well, if we zoom in, this is far from a rigorous justification. But if I zoom in on a patch here, maybe it starts to look like something we've seen before. So remember, the nice thing about our smooth surfaces is that if you zoom in, they start to look flatter and flatter and flatter. So if I zoom in onto this little patch here, and I think about what the flux of the curl is, all right, what do I mean by flux of the curl? So we see that in red is the curl of our vector field there. The flux measures how much it pushes through, the surface. Right, so that number on the left is big, right? The flux of the curl is big exactly when the curl points through the surface here. And remember what curl measures, right? It's kind of change of rotation, and it's orthogonal to where the rotation is. So at least it makes some sense that when we're measuring the flux of the curl, we're measuring kind of the spin of the vector field at each point. Which in the case of Green's theorem we saw could be looked at a rate of change of a line integral around a small section, right? And that's exactly what happens here, right? The proof, the justification we saw for Green's theorem that way, in just the plane, the xy plane there, where we looked at kind of a limit of a rate of circulation per unit area, gave us that scalar curl. The same thing happens here. It's a little tough to keep track of the dimensions there because you've got kind of circulation happening in 3 dimensions and packaging them all together. The details do get ugly. By all means, right? Read the presentation in Stewart, and I can point you to more rigorous treatments if you like. For this class, I'm more interested that you're able to state it correctly. You have all the objects correctly identified here, and you've got some idea as to why this works. So it makes some sense that on the small scale, the curl measures the circulation here. Well, if we add up the circulation around every box here and every little piece of this, notice we always get cancellation on the inside curves, right? So the flow of my vector field along this guy in one direction for around this little box is going to get canceled out by the flow to the left on the box below it, right? And this happens everywhere on the interior except when we zoom out. Right? If we add up those little curls of our vector field, right, times a little bit, all those little circulations will cancel out except on the boundary that have no neighbors, right, to cancel out. And so the result is just a one line integral around the outside. So you've got the double integral of the curl through the surface is equal to the line integral around the boundary of the vector field itself. I think of this theorem as adding up a bunch of little circulations on the inside, right? And everything cancels except the circulation around the outside. Another kind of application to kind of keep in mind for those so inclined from E&M, right? Fairly simple device like a solenoid right here. Now we don't apply it too directly here, right? But just as the first kind of intuition as to what's going on here. If you're familiar with a solenoid, right, and how it works, well, when you've got a coil of wire, right, and you run current through it, the magnetic field, right, which is orthogonal to the current, right, will point through, right, the kind of tube, right, the tube around which you wrap the wire. And the result is you can move, right, ferromagnetic things through that tube. And so a ton of devices use these solenoids, some very simple valves, right, where you can apply a current and close a valve using this. I think of them every time I enter a New York City apartment building and someone buzzes me up. What happens? They close the circuit, right? Current runs through the little wire, and the little whatever stopper thing it's called, right, that normally keeps the door locked, gets pulled back out. You can open the door, probably a little spring that sends it back when the current is cut off there. It's also the way speakers work, right? You got a magnet coil of wire wrapped around, you get the signal from your digital, from your music player, it drives current through the coil, that moves the speaker, that moves the air, that moves your eardrum, you hear it there. Right. Microphone works exactly the same way, it just reverses the process. Anyway, here's Faraday's law, which you may be familiar with as one of Maxwell's equation. We've got the change in the flux of the magnetic field, right, over here, negative change. I can never keep track of the signs in physics. But we got the change in the flux here is a surface integral, right, of the changing magnetic field. Right? Flux is the surface integral of magnetic field. So you can think of that as like the kind of surface cross section of one of these, cross section of this tube here. And then the differential form of Maxwell's equation says that change, right, the changing magnetic field, that's the curl of the electric field, right? It relates those two fields in that way. And then Stokes theorem tells you that, right, the flux of that guy here, right, this change is the curl of the electric field. So that's the same as the circulation of the electric field around the outside. So C is the boundary of D here, right? I don't think they're really changing in time despite that. Anyway, I don't mean to, right, go too far down the rabbit hole of electromagnetism, but I do like to think about this concept of, right, of circulation around being equal to a flux integral on the interior of it. And that's really all I want you to take away from this. So I'll keep this one short. We'll work many examples in class, as I said, and then we'll wrap up kind of the big picture vector calculus and send you on your way for final exams and beyond. So thanks. I will see you in class.